So this final test and final go is going to be the CO2. So I'm going to, like I told you, I was going to demonstrate several different ways of approaching data and phase boundaries. So this one will be the CO2 phase boundary. And then in the next video, we'll start filling out the phase diagrams for these gases. So final one, CO2. I'm going to make the same set of data folders. So real, BDW, perfect gas, and phase boundary. Which I think I'm going to now shorten to just phase for all of these. Okay. So now I'm going to put my red arrow in phase, just to, that's my starting point. Similar to before, I'm going to swap, all of my units and stuff are the same, so I just need to swap my fluid to carbon dioxide. So now that my fluid is at carbon dioxide, I can do the same thing, check all of my fluid information, which I already have written down for this fluid, but, and then check on the calculation. So for CO2, not unexpectedly, I have the melting line, the sublimation line, and the vapor liquid line. And that's because, well, it's CO2, so it's an important industrial fluid. It's an important supercritical fluid in industry. So it's been exceptionally highly studied. Okay, so we'll again, just as we did before, we're going to start with the dominant phase line for a fluid. And that dominant phase line for a fluid is always going to be the liquid vapor phase line. So now that I have a table up, I'm going to do the vapor liquid. Again, that I'm going to step from the triple point temperature to the critical temperature, stepping by 5 yet again. And I'm going to copy and paste those into Igor Pro. Temperature vapor, oops, vapor pressure, density liquid saturated, density vapor saturated. And again, I'm going to display this. So display P vapor versus density liquid saturated, and then append to graph P vapor versus density vapor saturated. Now here you can see the 5 is a little bit rough up at the top, so not quite enough points. So what I'm going to do now is I'm going to go back to the calculate saturation tables, and instead of doing 5, I'm going to do 2. Just recopy this and paste. And it's going to ask me, do I want to replace with 44? And the answer is yes. So now when I look at my graph, or redo my graph, now I have a much smoother transitioned line for the solid liquid. You'll notice though that it does not go to 0. Unlike all of the other gases we've looked at, it stops at 5. So 0 bar, this does not go to. And 0 density, it stops at 0.3. It also doesn't go to. So it looks like we have this gap, and that's because the vapor pressure at the triple point is 5 bar, not 0.01 bar or 40 millibar, or like the other gases that we've been dealing with. So now that we've done that, I can look and see, I still have the gap up here, so I'm still going to have to add those points down at the bottom. And I do that with calculate saturation points. This is going to be the from 302 to 304. So say 302.59, so 303. And since that's really close to the triple point, I'll do 303.1, 303.2, 303.3, 303.4, 303.5. Oh, 304.128. No, so 304.128. The critical density is 10.625. That's 30. There we go. So I will take those and add them to the bottom. And that gives me my smooth line at the top. Okay, so now that I've done that, and I've got this nice smooth transitional line, there's my phase boundary for liquid gas. Now, next thing we do is calculate saturation tables, solid liquid saturation. That's going to be from the triple point temperature to whatever temperature we want. The pressure limit for this is 800 bar. The density limit is 37.24. So we're actually quite a bit a ways from 37.24 in density. So let's see what happens with the 216 to 300 with 5. Okay. Did not. $216.592. Okay. Sometimes you should actually pay attention to the. There we go. And you can see at this point, notice the pressure. So I'm going to allow pressure to guide me here rather than temperature or density. So what I can see here is that the pressure is rapidly increasing. Now, for my experiments and my stuff, the maximum pressure my cell can hold is 450 bar. So I am going to stop at a temperature of 226.59, which is 495. So what I'm going to now do is go back and recalculate this table with a stepping of 1 and a temperature change to 226.59. And that's because I'm actually going to be stopping sooner than that. I'm going to stop at So 216.59. Leave active. If you hit the leave active button, it means I can add to this afterwards. Okay. Oh, not leave active table. So this allows me to get, looks like I could go a little bit higher. Just getting rid of tables I don't need. There we go. So calculate saturation table, solid melting, 226.592, and maybe I'll go ahead and take it up to 230. Okay. Now that gives me the option of stopping. Let's copy that. I really would want to stop at 450. So I'm going to do this one more time. And this is all about playing to get your stuff where you want it. There we go. That's better. Okay. So this is the temperature melting, pressure melting, density of the liquid at melting. I don't actually know the density of the solid, except I looked it up for the triple point. So pressure melt versus density liquid melt. Now, the density of the triple point solid, like I said, I looked that up online. I'm going to add it to here. So that's 216.592. We know that's the temperature. And the solid is 35 point, the pressure is 5.1795 and the solid is 35.4. So the solid density is there and would track, you'd end up with something similar to this curve. So that's kind of the two-phase region for the liquid solid. Okay, now our final one is our gas solid. So our sublimation line. So again, saturation table, solid vapor saturation. This would be triple point and colder. So again, I'm going to set the final temperature is the high temperature. So that would be the triple point, which is 216.592. We've already learned that. And right now we're going to step by 5 just to see where we're at. We're still at a pretty high pressure. So I'm going to go back to calculate saturation points. So take it to say 100. that drops our pressure. So looks like 150 is a good stopping point in terms of temperature and pressure. I'm looking for a pressure that's reasonably close to 0 if you're curious. And then I need to add the triple point data. So 216.592, that has a pressure of 5.1792. It has a gas density of that, which I've already written down. And then it has a solid density of that. So this would be temperature, sublimation, pressure, sublimation, and density of the vapor of sublimation. Again, we don't have the density of the solid and how that depends on temperature, but we at least have the density of the vapor. So and I will add that to, oops, that would be the pressure of sublimation versus the density of the vapor at sublimation. And that gives us this curve. So now you can see we filled in that. This is one of the few places where you can see this. But now here, you can see sublimation line, vapor line. And then over here, vapor liquid line, liquid solid line, liquid solid gas line. And there's the triple point. So now you find, this is one of the few ones where you can see it. Now, without a doubt, there would be an extension of this curve here if we had the density of the solid at the same time, but that curve would probably extend over here because the density of the solid is 35 and it would probably go, if I'm cooling, it might go down, but it might shift that way. But in essence, the solid behavior is, we don't really know it from the data that NIST RefProp provides, because that's just something that is not as well studied as the density behaviors for liquids and gases. So again, that gives us the phase diagram for CO2. I'm going to again hit Control Y to change this to CO2 phase diagram. And I'm going to again hit Control Y, CO2 phase data. That way I can, when I'm looking for tables, especially once this gets a lot more tables in it, I will have the ability to easily find which tables I'm looking at and which graph I'm looking at. And now I will save. So that shows 3 different gases in terms of creating the initial phase diagram, which is just the boundaries. In the next video, we will go back to ethane and begin to create the rest of the phase diagram for the real gas.